Welcome to Lesson 12F, Major and Minor Losses. We're going to continue talking about exhaust duct flows, major and minor losses. This should all be reviewed from your undergraduate fluids class, so I'll go over this fairly quickly. There's some difference in notation between fluid mechanics and HVAC, and I'll point those out, and then I'll do an example. Let's start with the steady state, steady flow energy equation. This is the version and in the notation of the Changao and Cimbala fluid mechanics textbook. This is in what we call head form. So all the pressures are expressed in terms of head, which has a dimension of length. This HL term is the total irreversible losses due to friction and mixing and stuff like that. There's the major loss due to straight sections of pipe. The minor losses are everything else, elbows, hoods in this case. We're talking about dampers or valves and things like that. This F is the Darcy friction factor, and then KL is the minor loss coefficient. V is the average velocity through the pipe or duct. I'm going to assume that all of you have used this equation in your fluids class. So first of all, for air, we typically ignore the delta Z. Since air is so light, the density rho air is very small. So cross off the Z1 and the Z2. There's never any turbines in any kind of HVAC duct system, so I can also cross off the turbine. Number 3, we have typically turbulent flow in our ducts. Remember that alpha is the kinetic energy correction factor. It varies with Reynolds number a little bit, but we're going to use 1.05 as kind of an average value for any of our flows. Remember that alpha, by the way, is the kinetic energy correction factor. That accounts for the fact that the flow is not one-dimensional flow, but it has some velocity profile to it, and that alpha accounts for that in the equation. Number 4, V is the average speed through the duct. Sometimes I'll use capital U. Those mean the same thing. And we know that Q equal V times A. So V is just Q over A, where Q is the volume flow rate. This term up here, H pump U, the U stands for useful. We always define in fluids as the useful head delivered to the fluid by the pump. It's a positive term because you're adding energy to the fluid in terms of a head that you're adding. And the notation is that a pump is a general term, but we typically associate that with liquids. You pump liquids. A fan is typically used for gases. And we're talking about air here, so we're going to call this a fan or a blower. Here in HVAC, we call it H fan U, useful fan head delivered to the fluid, to the air in this case. Number 6, in HVAC, we use C0 instead of KL for the minor losses. They typically have this as C0. Our ducts are often not round. In fluid mechanics, they're almost always round. Therefore, we need what we call the hydraulic diameter. We define DH, hydraulic diameter, is 4 times AC over P. AC is the cross-sectional area. Up here at Q is V times AC, and is the wetted perimeter. Now in pipe flows and water, you could have channels where maybe only certain parts of the perimeter were wetted. In other words, they're in contact with the fluid. For air, everything is in contact with the air because it doesn't have a free surface like water does. So the wetted perimeter in our case is always the total perimeter. And the idea of the hydraulic diameter is that we use DH in place of D everywhere. So you pretend that this is a round duct of diameter DH. And so all the equations will have D in them for Reynolds number and stuff like that. You just use DH and you'll be fine. Quick example, a rectangular duct in cross section. This is the width and this is the height. So we can easily calculate AC is W times H, and the perimeter 2W plus 2H. Therefore, DH is by definition 4AC over P is equal to 2WH over W plus H after a little bit of algebra. Number 8, the above equation is in what we call head form. That means that all terms have dimensions of length. where head is an equivalent column height of the fluid. With water, that makes sense. Water rises to a certain level, and we could call that a head. But in air, nobody talks about a column height of air. You can't visualize it, and it's not even that meaningful. So in HVAC, in air, we use pressure instead of head. You can still use the head equation, but it's not as physically meaningful as it is for liquids. Delta P is rho GH, remember from hydrostatics. So we want to multiply each term in equation 1. This is our equation 1. You multiply every term by rho G, and you could see, for example, this first term, you multiply by rho G, you're going to get a pressure. And everything else is in terms of head. Then you multiply by rho G, you're going to get a pressure. So multiply each term in 1 by rho G. So the steady state, steady flow energy equation for a control volume between 1 and 2, when you multiply by rho G, this becomes P1 plus alpha 1, 1/2 rho V1 squared. And that is actually a special term in HVAC. People like to call this the velocity pressure. We call that VP equal 1/2 rho V squared. I typed this all out to save some time. So this equation 1 becomes, and now we call it pressure form instead of head form. And again, I left these terms in, but we typically ignore those with air. Let's talk about major losses and minor losses. This HL consists of major plus minor losses. So let's treat each of those separately. All of you have probably seen the Moody chart. You calculate your Reynolds number. RE is rho V times D over mu, or VD over nu, where nu is mu over rho. Once you calculate the Reynolds number on the horizontal axis, you also have a roughness parameter. This is hard to read, but it's epsilon over D. Epsilon is the average roughness height, and you can pick off F, the Darcy friction factor from the Moody chart. Now, I don't advocate using the Moody chart other than to get a quick and dirty estimate. What I advocate is to use the Churchill equation. It is explicit. You don't have to do any kind of iteration or anything. So I will say use this for all calcs. I would strongly encourage you to put this equation into Excel or MATLAB or whatever, so that for a given epsilon over D and Reynolds number, we calculate F. And once you have that F, the major head loss is F times L over D V squared over 2G. Use hydraulic diameter when the duct's not round. L is the total length. So you can have a pipe, and then maybe there's an elbow, and there's another section of pipe, and then there's another elbow. You don't count the elbows, but you would count this length, and this length, just add them all up to give you the total L, if they're all the same duct, etc. Minor losses is everything else. In fluids, we use KL as the minor loss coefficient. In HVAC, we use C0. Either way, you look up in tables for various kinds of elbows and stuff, and I'll show you some examples. The head loss, HL, for these minor losses is equal to sigma KL V squared over 2G, or in our notation now, C0 V squared over 2G, where this is valid for all minor losses with the same V. And that's usually the case. So like this example, the V was always the same because you have the same diameter pipe. But you can run into situations where there are transitions where the pipe gets bigger or smaller. If the diameter changes, the Q will stay the same, but then V changes. And the rule is to always use the larger V for minor losses. I'll give you a quick example here. Suppose you have an expansion. There's a minor loss associated with this expansion, but since it's expanding, you have some, we'll call it VA, and then here the VB is less than VA. So using our rule, use the larger VA to calculate our minor loss. We can look up the KL and then we plug it into here and use that VA. Contractions are the opposite. VB is greater than VA, so you would use VB for that case. In terms of pressure, we would say delta P of the minor loss is equal to rho GHL is equal to sigma, I'll use C0, 1/2 rho V squared, or VP. So this is sigma C0 VP. I will do now an example. Air is drawn into a round duct. It's protruding from a wall, and there's a blower, but we don't show that. We're just interested in the duct right now. Total duct length is given, and the duct diameter. Roughness, this is our epsilon. The duct protrudes one diameter from the wall. There's the duct thickness. That's going to matter for the minor loss associated with that. They call it a reentrant entrance. There's elbows, and you can count them. 1, 2, 3. There's 3 of them. They're a specific kind, and I'll show you these. We'll find this on a table. I give you the density and the viscosity and the flow rate. We want to compare both the major and the minor irreversible losses. So here's our useful equations. This is in the head form. You're also welcome to use the pressure form. I'm so used to using the head form that I like to just do everything in head form and at the very end multiply by rho g. The first thing you need to do is pick a control volume. And most people would say, well, that's easy. You start here as 1, and then here would be 2. So you basically have a control volume around this whole pipe. Well, that's not the best choice of control volume. Is instead of just having it cross right there at the inlet, let's make a control volume that comes way out into the room like this. What we're saying is, let's call this one our inlet. Now, why do I do that? Because I know that way out here, the velocity is practically negligible. So we have V1 is 0 and P1 is P of the atmosphere. The rest of the control volume goes anywhere you want as long as it passes through the outlet here, which would be 2. This is very similar to what we used to do in fluids. You're draining water from a tank. So you've got this water surface here, and you have flow coming out, and you want to do a control volume analysis. Most students would make their control volume look like that, but that's not a wise control volume. It's better to make your control volume come around like this. This is a wise control volume, and you call this 1, and you call this 2. Otherwise, you'd have to calculate the pressure and the velocity there. Why worry about that when you know that up here, P1 is P atmosphere, and V1 is so small, we call it 0 because it's a big reservoir. The same thing is being done in air up here. So that's just a little trick, and then that V1 term is going to go away. A lot of times P1 and P2 are the same. They're both atmospheric, and those can also cancel out then. Let's do the calculations. Let's do the major losses first. The first thing we have to do is calculate the Reynolds number. So first I calculate V is Q over AC, and then we get about 12 meters per second as our average speed through the pipe. Now I plug that into the Reynolds number, and I get 1.845 times 10 to the 5th. Greater than 2300 by a large margin, so this is definitely turbulent. Epsilon over D, I get 0.001. So at this Reynolds number and epsilon over D, we can calculate F. From the Moody chart, just a quick and dirty estimate, I get F is 0.0211. This is 10 to the 5th right here. This is 2 times 10 to the 5th. So 1.845 would be somewhere about here. And so you come up until you find epsilon over D is 0.001. You go across, I called it 0.0211. It's much better to use Churchill equation. You get F equal 0.0213. That's the F I will use because it's more accurate. Then the major head loss is now, plug everything in, I get about 15 meters. So you'd have an equivalent column height of air that's 15 meters high.
What does a column height of air even mean, dude? It's not even a liquid.
It's the hydrostatic pressure that this column height of air would impart.
Oh, thanks, dude.
This is a head, but what we really want is a pressure drop. That's what I asked for. So delta P major is equal to rho G HL major. So when you plug everything in, you end up with 177.0 pascals. We'll call this delta P major as one of our answers. And then now I have to look at the minor losses. Minor losses, remember HL, minor. We need to sum up all the minor losses in the system. So we simply have to look those up. We had a reentrant entrance as one of our minor losses. Here's the diagram for it. In our case, we have T, the thickness over D, 20 millimeters over 230. So this turns out to be 0.0870. and L over D, it said it extended one diameter, so that's 1.0. So we look at an L over D of 1.0, which would be here, and we look at a T over D of 0.087, which would be somewhere in here. So we go across, we have to interpolate normally, but in this case, everything around there is 0.5. So fortunately, we could just say that C naught for that reentrant is 0.50. If you ended up somewhere in here, you'd have to do some interpolating. We also had these elbows, CD395 gore. Gores is these number of sections in the elbow. They're usually made out of sheet metal. 90 degree R over D, the radius of curvature is 1.5. And we had a diameter of 230 millimeters given. So we're using this column and we're using this row. And so our value is 0.21. So C naught per elbow equals 0.21 here. Again, there's no units. These are non-dimensional. Sigma C naught is equal to 0.50. We said that was for the inlet, plus 3 elbows times 0.21. And so that gives me 1.13. So HL minor is equal to sigma KL times V squared over 2G. And I come up with 8.343 meters. Again, that's a column height. So again, we actually want delta P minor loss equal rho G HL minor, 98.19 pascals. And then finally, the total delta P due to irreversible losses is delta P major plus delta P minor, 177.0 plus 98.2. These are all in pascals. So our final answer, delta P for all these losses, is equal to 275.2 PA at Q equal 0.50 meter cube per second. So just a preview of coming attractions. This is at one particular flow rate. We're going to recalculate this at various flow rates so we can see what the fan has to do to run this, and we're going to equate a fan performance with this system requirement. So we match available to required.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.